Welcome to Engineering Mathematics and Modeling Week 7. And today, before we go on with our topics on differential equations, I'd like to discuss a very short primer on complex numbers and a short extension of quadratic equations. Now, up till now, we've seen the real numbers, which can be denoted by the letter R with an extra stripe. And these are basically, if we have an axis system, is all the numbers from minus infinity to infinity, not including minus infinity and infinity. We also know that if we take the square of any of those real numbers, so if I have the real axis here, and I look at the function fx is x squared, that this function will be positive everywhere. So for a negative number, if I square it, I get a positive number, and for a positive number, if I square it, I also get a positive number. We see that there is no solution to the equation x squared is equal to minus 1. Now, this is, we can extend this system. We can go beyond the real set of numbers, and we can say, well, the solution to this is called j. In mathematics, we usually use an I for imaginary, and this is called an imaginary number, and this number j has the property that j squared is equal to minus 1, which then also means that minus j squared is also equal to minus 1. And this opens up a whole set of extra possibilities for working with functions and formulas and for us differential equations. So we can now write that the square root of minus 1 is equal to j. Now, as we know that the square root of a multiplication of numbers is the square root of the multiplication of two numbers, we can also now see that the square root of minus 4 equals the square root of 4 times the square root of minus 1 is equal to minus 2 times j. And any number of the form b times j is called an imaginary number. Now, if we add a real number, let's say a plus b times j, if we have the combination of a real number and an imaginary number, and this b is also a real number, so b here is in R, and here a and b are in R, the combination of a real number and a complex number we call, a real number and an imaginary number we call a complex number. And a will be its real part, and b will be its imaginary part. If we have a complex number, a plus bi, a plus bj, then it has a number that's associated with it, which is a minus b times j, which is called the complex conjugate. Now, there is a lot to tell about complex numbers, but for our purpose, this is all we need. Because we can now solve this quadratic equation. X is equal to j, or x is equal to minus j. And the question then arises, can we solve all quadratic equations of the form ax squared plus bx plus c is equal to 0? Now, if we wanted to solve this traditionally, we would look at the ABC formula, where the two solutions, x1 and 2, were equal to minus b plus or minus the square root of d divided by 2a, where d is b squared minus 4ac. This d could be positive, it could be equal to 0, and it could be negative. And if it is positive, we get two solutions. If it was equal to 0, we only get one solution. Well, actually, we get the same solution twice because it always has two solutions. And if it was negative, then we'd have to take the square root of a negative number. That wasn't possible. So then there will be no solutions. But if we introduce complex numbers, this can be changed. Here we get two solutions, and they are complex. So by extending the set of numbers that we know to the complex numbers, which is the set of complex numbers is denoted by C with a stripe, we can now solve all quadratic equations. So I'll give you an example. X squared plus 2x plus 5 is equal to 0. We'll use the ABC formula. x12 is equal to minus 2 plus or minus the square root of 4 minus 4 times 1 times 5 is 20 divided by 2. Well, we'll simplify this a bit further. Is equal to minus 2 plus or minus the square root of minus 16 over 2. Now this is typically where it broke down because we couldn't take the square root of minus 16. But now we can, because we know that is equal to plus or minus the square root of 16 times the square root of minus 1 over 2. Well, the square root of 16 is 4. The square root of minus 1 is equal to j. So we get minus 2 plus or minus 4 times j over 2 is equal to minus 1 plus or minus 2j. And we see that the solutions to a quadratic equation, if we have one solution, the other is its complex conjugate. So we have x is equal to minus 1 plus 2j, or x is equal to minus 1 minus 2j. So we see that these solutions are each other's complex conjugate, and if we have, we usually denote a complex number with z, and the complex conjugate is equal to z with a bar on top. It's not a vector, but it indicates that it's the complex conjugate. So we see that the solution to a quadratic equation yields complex conjugates. And now we can solve every quadratic equation, and it always has solutions. If d is equal to 0, you still get one solution. If d is if d is positive, you get two solutions, and they are real. And if d is negative, we get two solutions, and they are complex. Now we need this to continue our discussion on differential equations, but it will also pop up in other areas of math, and it substantially expands the problems we can now address. We will approach second order linear differential equations with constant coefficients, where we will need the fact that sometimes we have complex solutions to a quadratic equation.